Welcome back, Physics 30. This is the FI2.7, force on an electric charge moving in a magnetic field. So last video we looked at force on a current carrying wire, which guess what? Has electric charges flowing through it. So this is just kind of an offshoot of that. So apply the right-hand rule to determine the direction of the force on a charged particle entering a magnetic field. So we have seen that a current carrying wire experiences a force when placed in a magnetic field. Since a current carrying wire really consists of moving electric charges, we might expect that freely moving charged particles not in a wire would also experience a force when passing through a magnetic field. Free electric charges are not easy to produce in the lab as current in a wire, but it can be done, and experiments do show that moving charges do experience a force in a magnetic field. The direction of the force is perpendicular to the magnetic field and to the velocity of the particle. For a positive charge, the force is given by the right-hand rule again. You orientate your hand so your outstretched fingers point along the direction of the particle's velocity. So V, so the speed at which a particle is moving, is like the current. Because current consists of moving particles, so is velocity. When you bend your fingers, they point along the magnetic field. So if you recall, so your finger points in the direction of the current, or in this case, the velocity of the particle. Bend these fingers perpendicular to that. That's the direction of the magnetic field. And then your thumb points in the direction of the force. So use your right hand for positive charges that are flying, and you use your left hand for negative charges. So point in the negative whatever direction the negative is moving. These fingers point in the direction of the magnetic field, north to south. And the force is indicated by the thumb. So that's what's illustrated here. So this is true for positively charged particles. You use your right hand. For negatively charged particles, it's the opposite direction, or you can just simply use your left hand rule. So left hand for negative and right hand for positive. So magnetic fields compared to electric fields. Magnetic fields are somewhat analogous to electric fields studied earlier, but there are several important differences as stated. The force experienced by a charged particle moving in a magnetic field is perpendicular to the direction of the magnetic field and to the direction of the current or the velocity. Whereas if you look at electric phenomena, the force exerted in an electric field is parallel to the direction of the field. So a positive charge will move to a negative charge parallel. The right-hand rule in its different forms is intended to help you determine the direction of magnetic field, the forces, and the current or velocity. So the current and velocity can be thought of as the same thing of the particles. The right-hand rules are designed to deal with the perpendicular nature of that. So if you orientate your hand like this, everything is perpendicular to one another. And lastly, the equations in this chapter are generally not printed as vector equations, but involve magnitudes only. Right-hand rules can be used to find directions of vector quantities. So basically, there's three rules here, but really there are only two. So if we're looking at a current carrying wire, and we just want to know the magnetic field that's set up on that current carrying wire, if you recall, your thumb is in the direction of the current. So if it's positive current, such as a capital I, we use the right hand. So thumb points in the direction of the current, and our fingers wrap around in the direction. So if we had a bird's eye view, you can see that that is clockwise. So we have that. And last, if we looked at a current carrying wire, remember that your index finger points in the direction of current. If it's positive current, it's right hand. If it's electron current, we use left hand. Okay, so index finger points in the direction of the current. The other fingers, you bend them 90 degrees, so they point in the direction of the magnetic field, north to south, and then the thumb result shows us the force. And this current one really is the same one. Index finger points in the direction of moving charge. If it's moving charge, if it's a positive, you use right hand. If it's negatives moving, you use the left hand. And again, these fingers point in the direction of magnetic field, and the resulting thumb points in the direction of the force. So for example, let's say if you in the assignment you'll have a variety of scenarios. Let's say you have let's say it's a negative particle and it's going into the page, okay? And let's say the magnetic field line is going this way, okay? So negative, you're going to use your left hand. Into the page, the magnetic field is going to the right, so we move our hand so it's to the right. And what's your thumb doing? It's going up. So the force would be up. All right, so that's how you do it. So run through the assignment, check the answer key to make sure that you're on the right track. If you get confused with anything, just be sure to talk to me and we can hopefully clarify any right-hand rule, left-hand rule misconceptions. All right, we'll see you again.